All right, welcome back, everybody. I am Salvatore Fabiano, and I'm the editor of Trends in Endocrinology and Metabolism, and one of the organizers. And it's a pleasure for me to host the next session on metagenomics in AMR. So we have a little change in the program. Dr. Bertelli is not going to be here, so we're going to have Dr. Ruppe now, and then Dr. Loiseau, and we have a longer lunch break, and we will reconvene here at 2 p.m. So our first speaker for this session is Dr. Etienne Ruppe. He's an associate professor of bacteriology at the University of Paris and the Bishop Claude Bernard University Teaching Hospital in Paris, France. He works on a variety of topics spanning on various aspects of antimicrobial resistance, from carriage, diagnosis, infections, emergence, epidemiology, prevention, and information to the public. And today he will tell us more about antibiotic resistance detection in clinical metagenomics. Again, thank you.
Thank you, Salvatore, for the kind introduction, and thank you for the organization. So Claire will not be here, but I will address a little bit also the detection of AMR in metagenomics. I was afraid of a bit of overlapping, but this fear is now away. So today I'm going to talk about how to tackle antibiotic resistance in clinical metagenomics. So these are my disclosures for the last 5 years, and this is an outline. So I'm just going to recapitulate what we expect from clinical metagenomics in bacteriology, how to detect antibiotic resistant genes in metagenomes. Then we're going to address the challenge of from genotype to phenotype, from the DNA information to infer phenotype. We will show the proof of concepts in genomes and try to have clinical metagenomics in the bacteriological diagnostic. You know that, I mean, I'm a clinical microbiologist. I love my bacteriology. I like to culture bacteria, but let's face it, it takes time. And some of those bacteria, which can be very interesting, are very difficult to grow, and basically we do not meet them. So the fastest, I would say, time to get the results of identification of pathogens and antibiotic susceptibility testing is 48 hours, but sometimes when the pathogens are really slow growers, it takes longer, and sometimes the patients have been taking antibiotics and then we get no bacteria at all. So what we can do with clinical metagenomics is to try to go faster than culture. So with that, we have now very fast sequencing machines. And on the other hand, we can take the time in some situations like chronic infections, take the time to identify bacteria that would not have grown in the bacteriology lab. So it's mainly about identification. But then once you get an identification, the question of the clinician is always, all right, you provide a fancy name of a bacterium, but which treatment should I use? And then you just make half the way. And so you have to predict the antibiotic susceptibility from this genomic data that you will have, and you have to predict it with confidence because just downstream that there's going to be a treatment given to the patients. So there's lots of expectations in this antibiotic susceptibility inference. So how do we do that? So in metagenomics, but also in genomics, how can we identify antibiotic resistant genes, this ARG? So we need two things. The first thing is provided by the sequencing machines. You have your DNA and you obtain reads, which are very small pieces of DNA. Then you can have two strategies: use raw reads directly, or you can try to, like in a puzzle, try to assemble them into bigger pieces of DNA that we call context. And this is your material. Then you have to use a specific database for antibiotic resistance. And the good news is that we have plenty of them. I'm showing you here a summary of a review that's just been published last year. We have several antibiotic resistant genes database. And so the question is, which one should we use? So they're pretty different. Some have not been updated since years. Some are just combination of databases, just like Hershey Minor or Megares. Some have been collecting genes, not really from pathogens, but from metagenomic data. This one, for instance, is a database we published a few years ago, which is predictions of antibiotic resistant genes in the gut microbiome. So there's lots of possibilities, which I see as a positive point, because maybe according to the purpose, you can use different database. But just for clinical metagenomics, I'm sorry, I won't have any definitive answer of which one should we be using, just providing you some data. Indeed, they are very different in terms of content, but also in terms of scope. And I'm showing here some differences between CARD, which is very popular among bioinformaticians, and ResFinder. And you see here the antibiotic classes of CARD and antibiotic classes of ResFinder. If you're a clinician, I think you're pretty familiar with all these families here, but I guess that you won't be familiar with everything that's in CARD. So let's say typically that in CARD, you have genes which are not really genes that will have a clinical interest for you. And all the databases, one of the key message that they don't typically overlap because of the difference in the content that you have. So together with Rémi Gvin, the postdoc in the lab, we've been developing a database which is dedicated to collecting all the resistant genes identified by functional metagenomics, covering different environments, the gut microbiota, many anaerobic bacteria. And we did a comparison of this database with other popular databases such as the NCBI, which is Endaro, CARD, and ResFinder, and also Argonaut. And in this complex graph, but not that complex, you can see here when you have a black dot is that the gene has been detected. So for instance, in this line here for this category, all the genes, the 257 genes were detected by all the databases. But in that case, in this dot here, the 3,000 genes were only detected by CARD, and this relates to the very specific content of CARD. For us, for this new database, we had also lots of genes that were only detected by our database, which was expected because they were like exotic resistant genes from different environments. But just to see, my point here is that all these databases do not overlap. So maybe a good hand would be to combine databases to improve the sensitivity of detection. Once you've spotted your favorite database, or just combine them, then the other question is that how sensitive will I be in my bioinformatic method? If you're a little bit familiar with bioinformatics, sometimes for clinicians it's just a black box, but sometimes you get just interested to open the box and see what's just behind. And as for many clinical assay, you got parameters related to specificity and sensitivity. And in bioinformatics, you just tune that the way you want. I'm showing here the search for class AB lactamases encoding genes. It was in the gut microbiota catalog of genes. And we just tested the number of hits of the lactamases we got according to the E-value. E-value is a parameter for sensitivity. The higher it is, the more sensitive you are, but less specific. The risk of false positive is important. And the lower it is, the risk of false positive is very low, but you have a lower sensitivity. And you see here is just perfectly, it's just perfectly continuous that the more sensitive you are, the less specific you are. So what's the threshold we should use for clinical metagenomics? I would say that I want to be specific because I don't want to identify genes which may not be resistant genes. In that case, I could over-predict resistance, but I don't want to miss resistant genes because if I say, no problem, there's no resistant genes, you can use this antibiotic, but there is an antibiotic resistant genes that I miss. This is a very major error and that could have consequences. So again, I don't have any definite answer in that case. And we should not forget point mutations. I focus mostly on antibiotic resistant genes, but we should not forget also the genes in which mutations can lead to antibiotic resistance. This is the case we have famous cases like fluoroquinolones, rifampicin, fosfomycin. This is also a very important resistant pathway in mycobacteria. And I should say that in these antibiotic resistant genes databases, some addresses point mutations, but you see the, let's say the representations of pathogens is far from being exhaustive. CAR is very good in that, but clearly there are lots of bacteria missing. So I think there's still lots of work to do to cover all possible mutations addressing resistance to important antibiotics. So let's say we've spotted a right antibiotic resistant genes database, and we have identified resistant genes. So now how do we transform this data into phenotype, into phenotypic data? So it's just taking like bioinformatic data and say this strain will be sensitive or resistant to this antibiotic. To make the story short and to make a kind of a summary, this prediction at the genomic level, it works really well for Staphylococci, especially Staph aureus, Enterobacteriaceae, we'll come to that just a little bit in the next slide, Enterococcus, Campylobacter, and Mycobacterium tuberculosis. They are important pathogens, but you can see that the list is not totally exhaustive also. I should mention that ResFiner, the last iteration, the fourth one, embeds a phenotypic prediction, which is working for most of the bacteria mentioned here. But when it comes to other bacterium, such as Pseudomonas aeruginosa, I should also say Acinetobacter baumannii, then the prediction is not that good. Why is that? Because it comes to the issue of the expression level of genes. Typically in Pseudomonas aeruginosa, you have lots of efflux pumps, porins in which expression is underlying the level of resistance. And from genomic data, it's really difficult to address that. Also, one of the limitations is when the resistance is coming from mutations in multi-copied genes, such as linezolid resistance, in which one of the pathways is to have mutations, additive mutations in the ribosomal and coding genes, and using short-read sequencing and conventional assembly method, it's very hard to spot these mutations. So some authors have tried to address the Pseudomonas aeruginosa challenge, saying that, all right, we're going to combine what we know in terms of antibiotic resistant genes, point mutations, and we're going to also combine this with RNA sequencing, the expression level of genes involved in antibiotic resistance. And on top of that, we're going to use machine learning to try to mix everything and to make the best out of it. And so they use the data set of, let's say, with hundreds of strains of Pseudomonas aeruginosa for the learning data set and the validation data set. And the conclusion is that it's working better than just considering SNPs and the presence or absence of antibiotic resistant genes. But even with combining the gene presence absence expression of genes and SNPs, which is here in this category, you see that according to the data sets, you're not in this range where you should be if you want to use it as a clinical tool. So still lots of improvement for the bacteria such as Pseudomonas aeruginosa. So a few years ago in Jacques' lab in Geneva, we sequenced hundreds of Enterobacteriaceae, and we made a distinction between the cephalosporinase producers and the others. Why is that? Because the resistance to cephalosporins or to these drugs here, piperacillin, piptazo, ceftazidime, in a set of Enterobacteriaceae is driven by the expression of the cephalosporins, which is really hard to detect using genomic data. So we separate them and we said, if we do not have any mutation in the regulation gene of the cephalosporins, then we will say that the strain is susceptible. There's no expression. But if we were to see any mutation in this gene, we don't know what the effect of this mutation is, and then we're in the gray zone. We say to the clinician, no prediction attempted. We don't know. And I think this is an important message. Sometimes in bioinformatics, you have to say, I don't know, because I'm not confident in the data that I have. So that's what we say, that's what we've done. And it's like being humble, in front of all the biological pathways in bacteria. And in that case, we had some very good results for the bacteria not producing MC. We had very, very good results for prediction. And it was the case also when we could do the prediction in say, natural producers. And also, I think that's an important message in the metagenomic data set, that we can try to assemble this big puzzle and try to reconstruct genomes. And we have tools to assess the extent of the reconstruction of genome. And I think also that's an important point to know that if you have data supporting that you have not reconstructed the entireness of the genome, then you have to be very cautious in attempting any prediction. You have to say to the clinician, I've detected this pathogen, but I'm not well enough to make sure that I have or not any antibiotic resistant genes. In this data set, it was bone joint infection samples. We reconstructed the genomes of the pathogens we found. And this is the, let's say, the exhaustiveness of the reconstruction of the genome in percentage. And this is the concordance between the genotype and the phenotype. When the genome was reconstructed over, let's say, 80%, we would have a good confidence. But below that, we would have very bad results. So I'm not sure that 80% is the right threshold, but the concept of having a threshold below which you cannot report the antibiotic susceptibility results, I think this is something that makes sense. So it was a translation to clinical metagenomics. So we tried to do that also years ago in Jacques' lab using bone joint infection samples. And we had 8 samples in which we've identified only one pathogenic agent. So this is resembling genomics, right? Because you just reconstruct a genome, there's just one pathogen, and you're into this genotypic to phenotypic challenge, but at genomic level. So we had very good results to all the antibiotic was tested. We had still some major errors, meaning that we over-predicted resistance. That was because we had some additional anaerobic bacteria, which had some antibiotic resistant genes, so that we over-predicted the resistance compared to phenotypic data, culture data, in which it was only one, let's say, a conventional bacteria. We had only one very major error for bacterium resistance because of mutation we just overlooked. And when it comes to polymicrobial samples, it's becoming more complicated because you still have the major errors, identifying more bacteria than culture, so identifying more resistant genes, but also when it comes to polymicrobial infections, then you can have some bacteria found in culture that you will miss in metagenomic sequencing because there are other more abundant bacteria that were missed in culture. And in that case, you just miss the identification, so you miss the antibiotic resistant genes. So the performance are not that good. So just the future directions that's related to the latest results. How can we connect the antibiotic resistant genes with its host? Because you know that when you do libraries of metagenomic sequencing, you just burst everything, and it's very hard from bioinformatic point of view to reconnect the small pieces of DNA. You can do high-C ligations to cross-link of DNA within one cell, and once everything is burst, you can try to reconnect the connection you've done just before the preparation of the library. So this is an example of this high-C ligation in the fecal samples of 2 ICU patients. And you can see that they could nicely connect CFXA gene, which is a bit lactamase and colic genes found in anaerobic bacteria. It was found in Bacteroidetes, so it was fine. And oxantam were associated to proteobacteria, which is also true. But this is the phelum level. The phelum level is extremely high. So I would have liked, here to be associated with, I don't know, Bacteroides fragilis, for instance, and here E. coli. So we far from that, but that's a possibility. But, and this is fueling discussions, do we really need to connect an antibiotic resistant genes to pathogens? Typically, if we have an NDM in a sample, let's say a sample is supposed to be sterile, we will still consider genes whatever the pathogen that's bearing, right? So I think maybe this is relevant for samples such as respiratory samples in which you can have some background with the microbiota, but for supposedly sterile sample, maybe, I'd say that's my point of view, maybe it's not worth it. And what should we do with those anaerobic bacteria? Because one of the most frequent added value of clinical metagenomics is to provide new bacteria, and many of those bacteria are just anaerobic bacteria, which poses many challenges. What is the role in the clinical development and infections? Do we have to consider them in the spectrum of the antibiotics we give? And in that, if it's the case, how do we predict their susceptibility to antibiotics? For most of these bacteria, we know pretty much nothing because we cannot cultivate them in routine conditions. We don't know the resistant genes they can acquire. And for that, we have some databases of resistant genes, from anaerobic bacteria, but we don't have any phenotypic validation of those genes. Okay, So open questions. So that's it for today. So my take-home messages is that it's still a major challenge to predict antibiotic susceptibility or resistance in clinical metagenomics. We have lots of databases that have improved, but which ones should be used? Just one or just a combination of one? The genotype to phenotype works for many pathogens, which is good news, but still an improvement. It has to be improved for many other species, such as Pseudomonas or Acinetobacter. Should we make efforts to connect the antibiotic-resistant genes with the hosts? Is this a requirement for clinical metagenomics? What should we do with the anaerobes? Just asking you the questions. And it's still exciting times for clinical metagenomics. It's been, almost a decade that we have this clinical metagenomics new field, and there's still some work. So thank you very much. I hope I will see you today for the 8th ICCMG at the Campus Biotech. Thank you for CellPress for organizing such a wonderful meeting today, and thank you very much.